Hello, everyone. I am Toshiaki Koike from Mitsubishi Electric Research Laboratories, MAL, at Cambridge, Massachusetts, USA. Today, I'd like to talk about the new family of polar cores we call QC polar cores. First, I'd like to talk about the background of polar cores. Then we propose a new protograph polar cores. Specifically, we want to consider short cycle mitigations and how to design frozen bit location to achieve fully parallel, high gain, and low complexity polar cores. Then we want to further improve the performance using irregular QC polar cores. Then we want to summarize our talk. The next generation wireless communications envision a wide range of applications for Internet of Everything, considering environment, energy monitoring, industrial factory, manufacturing networks, building infrastructure management, medical and healthcare, and extended reality. For such IoE communications, we may need a stringent requirement in reliability, power consumption, and latency. In addition to wireless communications, optical networks also require low power, low cost, low latency, high density, and high speed communications, even greater than 1 terabit communications for data center networks. For such a data communications, forward error correction calls are very important. Classically, we use hard decision coding like Reed-Solomon BCH calls. More recently, we use soft decision capacity achieving calls, for example, turbo calls, low density parity check calls, and polar calls. Polar calls was proposed by Arikan in 2009, which achieves capacity in memoryless channels. It is a structured encoding and decoding architecture, then very flexible encoding rates using frozen bit selection. It has been adopted in 5G new radio standards. In polar cores, there is a polarization phenomenon by using a polar kernel, which takes the same reliability, then polarized to bad and good subchannel. Applying multiple polar kernels, which even produces very bad and very good subchannels. Then eventually, the proportion of good subchannels approaches the channel capacity. An original decoding method called successive cancellations has a log linear decoding complexity. It uses a specific message passing algorithm, collecting all likelihood message from the received signal. We first decode message bit U0. Then after decision of U0, we cancel to decode U1. Subsequently, we decode U2 and U3 in the order. The simple successive cancellation can achieve capacity, especially in long calls. It was significantly improved by SCL list decoding method in 2015. Indeed, polar code with SCL decoder can outperform state-of-the-art LDPC codes, especially for short block lengths and lower complexity regions. This figure shows the performance of state-of-the-art LDPC codes and polar cores at the relatively shorter cores. For all the cases here, polar cores can be better than LDPC codes. Here we consider 4 iteration BP decoding in LDPC and 4 list decoding for polar cores. Therefore, polar cores are very suited for short packet IoE applications. It is known that polar SCL decoding requires log linear complexity. It may be a major drawback compared to LDPC BP decoding, which is a linear complexity. This figure shows the per bit complexity versus the code block length for LDPC of the degree 2, 3, and 5. Polar cores is nonlinear complexity Hence, for long calls, polar decoding complexity can be higher than LDPC decoding. However, it turns out to be great advantage in complexity when we want to use short error correction calls. It motivates us to use shorter polar calls for low complexity. And using parallel coding, we want to achieve longer polar performance by using Protograph. The concept of Protograph was originally proposed in 2003 to represent a Turner graph in a compact version. For example, any 3-6 regular LDPC calls can be represented by only 2 proto-variable nodes and 1 check nodes, like this. One popular protograph calls is a quasi-cyclic QC LDPC calls using cyclic shift permutations. We can derive parity check matrix by using graph rifting procedure. Graph rifting uses replication of a graph and permutation of the edges. This is corresponding to a modification of parity check matrix by replacing 1 with Q by Q permutation matrix and 0 with Q by Q 0 matrix. A popular QC LDPC calls can be optimized by designing the cyclic shift value. It was known that the regular QC LDPC code has a girth bounded by 12. But later, it was shown that irregular QC LDPC code can achieve more than 12 girth. Using the concept of protograph, designing LDPC code became simpler. Now, we propose to use the protograph concept in polar codes design. Specifically, we apply the graph rifting for every polarization unit. So the generator matrix of polar codes, not the parity check matrix, is replaced by Q by Q permutation matrices like this. When using a cyclic permutation, we can generate a QC polar coding. For example, using this QC shift value based matrix, we can specify a 4-stage QC polar codes like this figure. Here, each polarization stage, there are circulant shift values associated. More specifically, polar units are first replicated by Q-fold in parallel. Then we permute across the exclusive OR edge. Then we obtain Q-bit parallel proto-polarization units. The most significant benefit of QC polar codes is the ability to eliminate short cycles in code graphs. In fact, conventional polar codes have a lot of short cycles. For example, 2-stage polar graphs here. There is a cycle for short loops in a message path. And in this example of 3-stage polarization, there are a lot of cycle 6 short loops in message path. Therefore, belief propagation decoding does not work well for standard polar codes. We use girth maximization method proposed in 2013. It can eliminate such short cycles by optimizing the cyclic shift values. Our proposed QC polar codes is a remarkable breakthrough to resolve a long-standing issue of loopy polar graphs. Let's first see the benefit by removing the cycle for loops in 2-stage polar codes. This figure shows the bit error rate performance as a function of SNR of standard and non-optimal QC polar codes. Using optimal QC shift values, we can achieve 0.9 dB gain because of the mitigation of cycle for loops. The gain can be more significant using deeper stage. This figure shows the 4-stage polar course of standard case having no lifting. By increasing the lifting size from 1 to 256, we can achieve 2.5 dB gain. More importantly, it does not increase the bitwise complexity. Here we consider a long block length of 2 to the 16 bits. For 6-stage polar cores, we can improve the performance by using QC of 1024 significantly. Remarkably, this is even better than 16-stage polar cores using SC decoder. For 8-stage polar cores using QC 256, we can achieve the performance comparable to a 16-stage SGL decoding. Because of the reduction of polarization stage, we can achieve lower complexity decoding. We actually need to optimize frozen bit location for BP decoding. Conventional approach is using Bhattacharya parameter. It was improved by density evolutions, quantized density evolution, or Gaussian approximation. Recently, the beta expansion was proposed, but all are for specifically SC decoding. More recently, genetic algorithm, deep learning, and extrinsic information transfer were used. In this talk, we extend to use Protograph-Based analysis for both SC and BP decoding. Protograph-Based was originally proposed in 2007 for QC LDPC code design. It tracks mutual information updates at all edges, accounting for edge connections. Then it is more accurate than conventional ISIT chart. For example, those two codes have the same degree distributions. However, B1 is better than B2, and conventional ISIT chart cannot predict which one is better, while P-ISIT chart can analyze accurate threshold. We use this P-ISIT to optimize frozen bit location by tracking the mutual information updates over plot check nodes and plot variable nodes to predict the error rate performance. We further improve the performance by introducing irregular QC polar cores by jointly designing frozen bit location and deactivation of polar units. The irregular polar cores was proposed in 2017. In a polar graph, polarization unit can be represented by factor graph. Here there is a check node of degree 3. And then if we prune the edge of check node to be degree 2, it becomes no computation in a graph. Then we can reduce the computational complexity for encoding and decoding latency, and also bit error rate. The benefit of irregular polarization was verified in our previous papers, as shown in this figure. But applying irregular polarization for QC polar cores, we can achieve another benefit to directly remove short cycles. Now let's demonstrate the benefit of irregular QC polar cores. This figure shows the bit error rate performance as a function of the number of pruning units. For the 4-stage polar cores, removing protopolarizations can degrade the performance. However, it is still better than standard polar cores until 64% reduction. More remarkably, for 6-stage polar cores, until 7% reductions, the bit error rate performance indeed improved from the regular QC polar codes. It shows a potential to reduce the complexity and error rate at the same time. Now let me summarize the advantage of QC polar codes. We can increase the girth to enable VP decoder competitive with SCL decoding. Then we can fully parallelize encoder and decoder. We can achieve lower complexity equivalent to Q-fold shorter polar codes. Yet shallow polarization achieves competitive performance of deeper polarization. The shallow polarization can simplify the code design, and it achieves non-power of 2 code word lengths. We can also use irregular polarization to improve the performance. More importantly, many well-established techniques used for LDPC codes are now applicable for QC polar code design. Our work can open up a new research field of polar type generalized LDGM codes. Now let's summarize our talk. We proposed a very new family of polar codes called Protograph-Based QC polar codes, which has many advantages. We highly envision that the QC polar codes can stimulate the research community to investigate many fascinating topics bridging LDPC and polar codes. For questions, feel free to contact me. Thank you so much.